Well, traditionally at the end of the learning sequence we are going to talk about how to do some things in R, and I will use the same example with engineers that I used for the video lectures. I have two files, engineers 50 and engineers 150. So in the first file we have data about 50 engineers, and the second is about 150 engineers. Okay, you can get these two files either from Moodle or from the EDX platform. So let's start with 50 engineers. So I'll just get the data. In this case, I just need to specify the file name, engineers. Okay. So that's the data. You can see that we have 50 observations and 2 variables. If you open it in the, you can see that the variables, in fact, it's a factors. Okay, so I have no or yes for knowledge of R, and then I have salary with levels high, average, and low. And then you can see that these both variables are factors, in fact. Okay. So the first thing we need to do is how to calculate frequencies and how to calculate proportions and how to visualize frequencies and proportions using different plots. Okay. So we use function table actually to get the frequencies. So for example, frequencies for knowledge of R, you can say table and then $, and then knowledge of R, null R. Then the same for the second variable, salary. Okay, and then we can display both show F1, show F2, show F2. Okay, so if I run it, so you can see that this is the frequencies for the knowledge of R, and then this is the frequencies for the salary values. Okay, then if you want to calculate proportions, you just divide these values to the total number of the answers. So like I do it here. So, and then I can also show you the proportions. So you can see the proportions. We have 0.6, 0.4, and then we have 0.48, 0.28. Okay. So, and then if you want to visualize that, you can make a bar plot. In the simplest case, you just specify the vector with frequencies, and then because we already have the names for the values, you can see that the bar plot shows the correct names. So we have 30 engineers who answered no, and 20 engineers who answered yes in this case. Okay. And then you can also make a bar plot for the proportion, of course. It will look very similar. It's just the axis which is different now. So it's 60 and 0.6 and 0.4 in this case. Okay. Yes, and because the bar plot is just a plot, you can change any parameters. For example, you can change color. You can add, for example, X label, knowledge of R, and it will look like this. So you can also add boxes. You can do a lot of interesting things. Okay. And then the same, of course, for the salary. I'll just take this one. Then I will use F1 here, F1, F2 here. Then the same color, but then in this case it's a salary. So you can see the 3 plots: average salary, high salary, and low salary. Okay. Well, if you want, you can make pie charts as well. It's a function pi that does it, and the same idea. You just specify either, in this case, either the frequencies or proportions. The result will be the same. Okay. So that's the pie chart. And then if you want to change, for example, a color for a pie chart, you just simply say specify as many colors, as many labels you have. So in this case I have, for example, red and green. And of course I need to use small letters here, red and green. So you can see first is red and second is green. Okay. Then we can make a pie chart for the second case as well, and then red, green, and let's say blue. So that's the pie chart for the second case. Okay. So that's relatively easy. You can also add labels. You can also add titles. Look at the help for function pi and bar plot if you want to get a little bit more out of it. Okay. So this is how to visualize the frequencies and the proportions. Now let's talk about how to make a test for proportion. So the function that does everything is called prop test, and it has 2 main arguments. First of all, it's how many counts you have for the given level. For example, if we want to make a test for the proportion, of engineers who don't know R. We know we have 30 engineers who don't know R. And the second value, it's a total number of values. In this case, it's 50, right? Then we just run it, or we can also assign the results to a particular variable and then show the particular variable. Of course, it will be the same. So you can see that we have 30 out of 50, and it always assumes that the null hypothesis proportion is 0.5. I'll show you how to change it a bit later. Then this is the p-value, so it means that that's the chance to get a sample like we have, or even more extreme, if in fact only 50% of engineers don't know R. Okay. Then it also calculates the confidence interval, so that's the confidence interval for the engineers who don't know R. And then if you calculate it manually, you can see of course the same. Okay. Then if you want, for example, to do the same for the engineers who know R, you just substitute 20 to 50, and then that's the test. So that's the confidence interval, and so on. Okay. Now, what to do if you want, for example, to make one-tailed test? Well, it's a similar thing as we used in the t-test. It's just a special argument which is called alternative. For example, can we be sure that at least 50% of engineers know R? In our case, it's 20 out of 50, and then by default we have 0.5, and then the alternative will be so we have smaller, right? So less. Okay. So that's the p-value. That's a chance to get a sample like we have, or even more extreme, if in fact for the population, at least 50% of engineers know R. So you can see that chance is quite a big, 10%. Okay. Then if you want to change this, for example, you want to test if at least 60% of engineers know R, then you just provide the pi which you want to make a test for example, 0.6. So in this case, you can see that the p-value is pretty small. So we can't say that the sample came from the population where at least 60% of engineers know R. Okay, so that's how to make a test for proportion and calculate confidence intervals. Now let's discuss how to make the association test for association. Okay. Well, first of all, you can calculate observed frequencies using the same function as we used for proportions. As function table, you just provide a data frame with two vectors, with two categorical variables, with two factors, and then you can see the frequencies. So that's the frequencies, and you can see that because we have knowledge of R as a first column and salary as a second column, it uses rows for the knowledge of R and columns for the salary. If you want to do it vice versa, like we did it in lectures, you can transpose the table with observed frequencies, and then you can see that if I run this code, now we have knowledge of R in columns and the salary in the rows. Okay. Then if you want to make a chi-square test, the test for association, that's how to do it. The function is called chi-square test. Remember, we use chi-square distribution in this case, and then you just provide the observed frequencies. Now, if you run the test, you will see a warning, and it says chi-square approximation may be incorrect. Okay, you remember we have this rule that the frequencies, it should be at least 5 frequencies for every item, right? In this case, the chi-square association will be correct. And if you look at the observed frequencies, indeed, you have at least 5 here, right? So you have don't have any combination that is less than 5. But the problem now it's expected frequencies. If you look at the expected frequencies, I'll show you in a minute. We have at least one value, it's 4.8. So that's why we have this warning. So in this case, it's not a big deal, but actually it's important to have a proper sample size when we use a chi-square test. Okay. So that's the result of chi-square test. So this is the chi-square or chi-square. This is the chi-square statistic, and you remember in the lecture we had exactly the same 2.9. This is degrees of freedom, and this is the p-value. Okay. And then this function res, it gives you a lot of information. In fact, you can get the expected values, the expected frequencies also as a table. Okay. Then you can see we have this table exactly the same as we had in our lecture, and then this is the problem. Okay, so we have the expected frequency for engineers with low salary and no R is 4.8, so it's below 5, and this is why we got this warning. Okay, you can also see the standardized residuals. You don't need to calculate them manually. Just it's called, I think, STD res. Don't mix it with residuals, because we have residuals, it's just a difference, and then we have the standardized residuals. So these are standardized residuals. Again, if you compare it with the table that we got in the lecture, we have the same values here. Okay. So that's how to make a test for association. And then if I just run all the script for the second data set, so engineers 150, you can see, for example, that the counts, of course, are different. Now we have 3 times more answers, but the proportions are the same. So you can see we have still 60% who don't know R, 40% who know R, and then 48, 28, and 24% for the salaries. Okay. Then, of course, the bar plots and the pie charts will be the same because the proportions are the same. Okay, and it makes no sense to make any proportion tests in this case. However, if I do that, you can see that I will get slightly different p-values because the sample size is different, and the 4 p-values and confidence intervals will be different as well. I will skip this part. Okay. Now, if you look at the observed frequencies, so this is the observed frequencies for the new data set, and if we make a test, you can see that in this case the p-value is very small. It's 0.01, about 0.01. So it's 1% chance to get a sample like we have, or even more extreme, if in fact the sample came from population where there is no association between the level of salary and the knowledge of R. Then we can also see the expected frequencies. In this case, we didn't get any warning message because we have a sample size large enough also for the expected frequencies. Then these are standardized residuals. Again, you can see that they look the same as we have calculated in the lecture. And then for the relative risk, there is no built-in function for the relative risk, but there are many different packages where you can find functions that are already written for you. And of course, you can always do it manually as well or write your own function. So let's use one of the packages. It's called FMSB. Let's install it first. So FMSB, then install. Okay, just wait a bit. Yeah, here we go. Then we load it to memory using library FMSB. Okay, and then there is the function that we need is called risk ratio. This one. So you can see how it looks like. So you have to provide 4 numbers at least. The first, it's number of disease. In this case, it's because it's made for the doctor, so that's why it's called disease, but you can actually provide anything else. So the number of disease occurrence among the exposed cohort, the number of disease occurrence among the non-exposed cohorts, the number of individuals in total. Let's try some funny example. You probably will not find it funny, but I'll do it anyway. So let's say that we have 50 students, so 50 students and 50 students who attended the seminars and 50 students who did not attend the seminars. Okay, and then 5 students out of the first cohort who did not attend the who attended the seminar. So I'll just write it: attended seminars, did not attend. So let's call it group A and group B. Okay, and then 5 students who attended seminars did not pass the statistics exam. Okay, but for those who did not attend the seminars, this is 15. Okay, so let's calculate the relative risk and confidence intervals to not pass a statistic test if you did not attend the seminars. I must say a disclaimer that, of course, in fact, it will not influence you directly. So it's just an example. Okay. So the relative risk, in this case, so we have 5 and 5, and we have X and Y, and then we have N1 and N2. I use N instead of M. It doesn't matter actually. Okay. Then I keep the confidence level and the p-value is the same. Then I can show the results. Okay, so let's calculate it. So this is the results. You can see that the exposed, non-exposed, disease, non-disease, of course, in this case, we don't have any disease. So it have exposed means those who attended seminars, non-exposed, it means those who did not attend the seminars. And then disease means did not pass the statistical exam, and non-disease means pass the statistical exam. Okay. So if you show the results, you can see some interesting things. So you can see the p-value. It's a chance that the risk we see in this case is significant, right? So we compare it with 1 where there is no risk. Okay, this is the confidence interval. So you can see that the relative risk not to pass the exam if you attend the seminar is less than 1. Okay, it's less than 1, so it's between like 0.13 and 0.84. So it means that attending a seminar decreases the risk of not passing the exam. Okay, if you want, you can calculate also the vice versa. So we can just change y and x here, and then it's not necessary to change n1 and n2, but I'll do it anyway. So now you can see this is the risk. So now the risk is 3. So it means that the risk not to pass the statistical exam if you don't attend the seminar 3 times larger in our sample than if you attend the seminar. And that's the confidence interval. So you see that not attending a seminar gives you a risk not to pass an exam at least by 1.17. Up to 7. We don't know the real value, but for our sample we got it 3. Okay, so that's how to calculate the risk ratio and to make an inference for the risk ratio. Okay, so now you know how to work with qualitative data, and hopefully we'll be able to use this knowledge for your own projects as well.